Let me answer you one's question first, and I'll answer your question, okay? So you would ask, could you give an example of starting with conclusion? Yes, I'm about to do this example. After we did this, you should be able to know what I meant. So here is an example. Can you guys see my screen? Or no? Okay, cool. So here is an example. They want you to use the grading scheme to grade the following proof for the fact that for all even and a natural number, 2 to the power of 3n minus 1 plus 5 times 3n is divisible by 11. Okay, so you need to prove this. Here is a rough proof. I want you to rate this and use the grading scheme to tell me what mark would you give to this proof. How can I? So grading scheme, let me make it small. Actually, this is hard. Okay, everyone take a screenshot of the grading scheme. Ready? Can I move to the proof? Actually, I can do it myself. Let me take a screenshot. Okay, here. And put it in the chat. Oh, someone got it. Anyway, and then I want you to rate this proof and decide what mark would you give to this proof. Okay? And from there, I'll tell you what does starting with conclusion mean. Give you some time to work on this. So it's out of 4. Once you're done, you can tell me what mark would you give to this proof in the chat. And I will tell you what mark would this proof get if it's on a quiz or a test. Okay, I see everyone said 2. And that's not right. 2 is not right. Right, let's take it up. So, everyone said 2. Someone tell me where exactly did you deduct mark? Where exactly did you deduct those 2 marks? Anyone? I didn't prove for base case and assume for all natural number. Okay, so someone said here, didn't prove base case, so base case is wrong. And you said assumed for all, so here it's wrong as well. And start with conclusion in proof. Are you talking about the this or this? Base case or induction steps? Induction step is fine. Induction step is actually fine. Base case is incorrect, that's right. And I'll tell you, this proof will get 1 out of 4. So there is another mistake. N has to be 1, no. They said even N. Okay, so we're proving for even N. So the base case is 2, that's correct. Don't we have to use K? You don't have to use K. Where is the other mistake? Anyone? Read your marking scheme again and tell me where is the other mistake. It's right in front of you. I'll tell you why it's wrong. It's not TA training. I let you to do this so that when you write your own proof, you know where to avoid common mistakes, right? Well, but if you're doing well in this course, I encourage you to apply to be a TA as well. Actually, some of my students became a TA after. Yeah. Anyway, the other mistake is here. P of n. Okay? That's the other mistake. Okay, I will answer all of your questions later, but let's start from the beginning. Why is P of n wrong? Okay? Let's go back to the principle of mathematical induction. So let's go back here. Remember what your PM is. Let PM be a mathematical statement. Then Pn is true for all n in natural number, which means you need to show Pn is true for all natural for all n in natural number, but here they are saying that Pn is for all n in natural number. This is divisible by 11. So that's the wrong part. You don't have this in your Pn. Okay? You want to show Pn is true for all even n in natural. You don't put this inside. So your Pn would be 2 to the power of 3n minus 1 plus 5 times 3n is divisible by 11. That's your Pn. So that's the first mistake. Okay? Let me put it here. So here minus 1 because Pn is wrong. Second, someone asked me why the base case is wrong. So let's go back to the marking scheme. The marking scheme says that proved the base case explicitly and correctly. Do not award any points if the student starts with a conclusion and then derives a true statement. That's where the mistake is, because the proof started with a conclusion. So that answers one of your question. Okay, I don't remember who asked that, but that answers here. So for your base case, what you need to prove is that you need to prove when n equals to 2, 2 to the 3n minus 1 plus 5 to the 3n is divisible by 11. But what this proof did is that it started with that we know this is divisible by 11 already, but we don't. That's what we need to prove. So this is what we need to prove. What we need to prove. But this proof started with what we need to prove and derived something that's true. Okay, it's the other way around. Or you need to actually put 2 in there and get a number to get this is divisible by 11. Okay, so this is only rough work for the base case. That's why it's wrong. Okay, so here is another -1. Please do not make those common mistakes. Yes, you just plug in 2 and get a number, and you can see that number is divisible by 11. You don't do this. Okay, let me see questions. The induction part started with conclusion and get to the statement that's verdict. Isn't that wrong? We'll talk about induction step later. So we prove this step by deleting the right side. No, we'll talk about induction step later. Would it be true if the 11k were removed from each line? Yes, that will be okay. Okay, so the actual proof you need to do is you plug in 2. So 2 to the 3n minus 1 plus 5 times 3n equals to 2 to the 6 minus 1 plus 5 times 3 to the 2, which will give you 32 plus 45, which equals to 77. And we know this equals to 7 times 11, so this is divisible by 11. Okay, that's good. Which is divisible by 11. So you cannot assume it's divisible by 11 since the beginning. You have to show that it's actually divisible by 11. Okay, so that's base case. Inductive hypothesis. So let's look at the inductive hypothesis. Now assume that Pn for all even n in natural number. Why is this wrong? What happens if we assume this? Why do I use for some? Not why is for all wrong? You guys should think about why do I do such things. Don't memorize anything. Because we only proved for 2. Not necessarily. Guys, you should think about why do I use for some, not for all. Why is for all wrong? Yes, exactly. That's what you are trying to prove. For all is a conclusion. Okay? So if you assumed for all even and in natural is true, then what's left for you to prove? That's what we need to prove. That's why you cannot assume what you need to prove. Okay? So you assume for a particular n or for some n is true, and you need to prove for all. So that's why it's wrong. Yes, exactly. Okay? So here -1. Okay, some of you ask why is the induction step correct? So let's look at the induction step. So the induction step, we need to show that, another thing I think one of you mentioned is that why are we using n here instead of k? You can use k as well, it doesn't really matter, okay? You can use k as well. So you can say assume pk for some even k in natural number. That's all right. But if you use k here, make sure you use k everywhere after. Okay, so those have to all be k. But if you use n, that's fine as well. Doesn't really matter which one you use. I personally prefer k, but it doesn't really matter. It really doesn't matter. Anyway, induction step. So what you need to prove is that you need to show p of n plus 1 is true. So we need to prove p of n plus 1 is true. Oh, n plus 2, sorry guys, n plus 2, because we're talking about even number. So since n is even, n plus 1 will be odd, so we need to prove p of n plus 2 is true. Because the next one, this is a variation of induction. I just want to use it to show you the common mistake. But the thing is, like, this, so basically you need to show this whole thing is divisible by 11. In this proof, he didn't start with this. Okay, he didn't start with this equals to 11k. So he did not start with assuming this is divisible by 11. Instead, it's showing you step by step why it's divisible by 11. So this induction step is fine, except for inductive hypothesis, you need to specify where exactly you used it. So where did we use inductive hypothesis? Step 3. Step 3, are you talking about this line? Or the next line? Nine times 2. Oh, this line, the next line. You're talking about this line? Right? Yes. Close enough. But this line, as you can see, this line didn't really do anything. This line is just grouping this around. What actually used is the next line. When you write this as 11m, that's when you used the inductive hypothesis. Okay? So here you should add by IH. Make sense? Because this line, when you write it as 11m, that's when you use your PM as true. Okay, so that's when you use this is divisible by 11. Okay, so after we correct it, now it's a good proof. So those are the common mistakes I hope you guys don't make when you write your test. Since I'm giving you the marking scheme, it's most likely we will use the same marking scheme if the induction question is worth 4 marks. So when you write it, remember the common mistakes I talked about. Don't make the same mistakes, okay? Screenshot, sure. Not sure if you can fit everything though. Okay, I think this is good. Yeah, it's on Discord too. Oh, are you talking about step 1 or why PN is wrong? Oh, again, I said PN, you should not include this. The quantifiers should not be included in PN because you want to prove PN is true for all even and unnatural. If you leave it in, it's like redundant. For even numbers, we start with base case n equals to 2. Yes, because even numbers are 0, 2, 4, 6. It's even natural, so we start with 2. And proof for k plus 2, yes. Well, you'll never get some questions like this because that's variation, and you guys will only be tested on simple induction. In PN, you don't say that. When you write PN, you don't involve any quantifiers. Okay? You don't, this whole thing is your PN. You don't write any quantifiers in there. Variation is like, for example, when your base case is not 1, So when your base case start with 2 or 3 or 4 or something, that's one of the variation. Another one is when they ask you to prove even integers or even natural numbers, odd natural numbers, such as this one. So that's another variation. Another one is strong induction. Okay, strong induction is another variation of induction. Also, something like recursive sequence. Those are variations as well. Right? Okay, we will do more induction questions. I'll give you time to do induction question yourself. So here is an example. Someone said let's do inequality. We will do that as well. Okay, later I'll pick some inequality questions for you to do. We'll do that. We'll do that. On the test, no. Those are variations. You might see them on your exam, but not on your test. Let's try this question. So we'll do 2, 3, and then we'll do more induction, like other induction, such as inequality ones, okay? And we'll go back to other questions. Because I remember one of you asked me to do image questions involves Cartesian product, so we'll do that as well. I will try to cover all the topics that might be on your test, and we'll do a lot of questions, okay? I'm not sure actually. Let me see. Let me check 4.1. I think that's just simple induction. Yeah, it's just simple induction. Yeah, up to 4.1, not just 4.1. So chapter 1, 2, 3, and 4.1. You'll be happy. They can give you really hard induction questions. Pn equals to n cubed plus 2n is divisible by 3. Where did you get n? Oh, I see. The first one is right, the second one is wrong. Why? Because divisible by 3 means equals to 3m, where m is an integer. Not natural number. But if you write where m is an integer, that's correct as well. So guys, try this out, write the full proof, and you can grade yourself based on the marking scheme, okay? This is simple. Yeah, this is simple induction. I don't plan to do any variation, to be honest, because I just want to prepare you for the midterm, right? So we'll do variation after. We'll do it next week. We'll do other induction questions next week, but not today. At least not before your midterm. Plus 2. Didn't you say we shouldn't write the quantifiers for P? I didn't write quantifiers for P. Where did I write quantifiers for PM? I don't have quantifiers for PM. This is my PM. Okay. I don't have quantifiers. I did not say for all natural. Oh, this is not a quantifier. Quantifiers like for all there exists. Those are quantifiers. N is a natural number that's just defined N. Okay? And I wrote it outside of my PN. If you put it inside, that's okay as well, but yeah. Here we didn't need to do, okay, we could. You could do that as well. Okay, let me answer your questions. Do we have to say 3 times k squared plus k plus 1 is a multiple of 3? It's better that you say it. So it's better that you say this is divisible by 3. But I would say let's be safe, so let's all say it. Because I don't know who's gonna mark the question. I don't know what the marking scheme is gonna be, so let's just be safe. Let's all say it's a multiple of 3, or it's divisible by 3. Here we didn't need to do k squared or k cubed plus 2k equals to 3m. You could do that just like in the other proof, like this. But you can also just say it like what I did here. By IH, we know it's divisible by 3. Okay? So this line, and write it as 3m, that's the same thing. It's equivalent. Our point is just saying that this term or this expression is divisible by 3. Okay? Any other question? Any other question? Could you go to principle? Okay, let's go back. Here, why it states for all n belong to n at the beginning of the proof. At the beginning of the proof? You mean here? Oh, this is saying for all n in natural number. So this is saying that our n here is natural number. So this means that P1, P2, P3, P4 till whatever, because it goes to infinity. Okay, so all of those P's, they're all mathematical statements. That's what it's saying. Does that make sense? Oh, also this is not a proof. This is a principle itself. So I do not suggest you guys to memorize anything. Please try to understand why we're doing each step, because memorizing is not gonna help you on this course, okay? Any other question? All right, no question. Let's do another example and we'll do inequality after this example. So what happens if the base case fails? You try the next one. So if m equals to 1 doesn't, it fails, then you try m equals to 2. If it fails, you try n equals to 3. But in that case, it's not for all natural numbers anymore. So if your base case is not 1, you might get like n equals to 3 be your base case. Then what you proved is that for all natural and greater than or equal to 3 is true. But you will not get that for your test. You will not get that for your test, okay? Go up a little. Oh, okay. Here. you don't need to copy down anything. You can just take a screenshot. And I can also upload it after. I can upload this Quarkus after it's done. Okay, so guys, try example 3 and I will find a good inequality example for you guys to do, okay? Try example 3 first. Okay, I will upload it after. It's okay. 4.6.2b, we can do that. I just want to make sure it's the reason I don't want to do textbook questions is that I don't know if it's gonna be on your problem set later. So that's why I try not to do textbook questions. But we can do it. Sure. Okay. Let's just do question example 3 first and we'll do a inequality question. Suppose PK for some K in natural number. Actually, I want to write it in this way. Let's talk about it first. And I'll continue writing while we reach the point. So again, first of all, you need to tell me what your P of n is. So basically, you just need to remove the quantifier, and what's left is your Pn. Okay, so it's 1 times 2 plus 2 times 5 plus n plus 3n minus 1 equals to n squared plus n plus 1. This whole thing is your Pm. Now you do base case. Base case is 1 n equals to 1. So your left hand side is 1 times 3 times 1 minus 1, which equals to 2. Your right hand side will give you 1 square times 1 plus 1, which will give you 2 as well. So we reached left hand side equals to right hand side, so our base case holds. IH, you suppose pk for some k in natural number. So this basically it never changes if you write if you define your pk or pn. Okay, basically it's always this. Now induction step, you need to show pk plus 1 is true. So let's write down pk plus 1. 3k minus 1 plus k plus 1 times 3k plus 1 minus 1. So this is the left hand side. We want to show the left hand side equals to the right hand side. This, can someone tell me what's the next step? What does this equal to? What can we use right now? We use the IH. Exactly, okay? We use the IH. The IH is saying that this whole thing, okay, this part equals to k squared times k plus 1. Plus k plus 1 times 3k plus 3 minus 1 is 3k minus 2. Wait, 3k plus 2. Okay, this is IH. By IH. We can use this because this whole thing is from your IH. Okay, I didn't write what P of K is, but you should know what it is, okay? So now you can simplify it. The rest is just algebra, okay? So this equals to k plus 1, k squared plus 3k plus 2. So 3k k squared plus 3k plus 2 k 1 2. Yep. So that's k plus 1, k plus 1, k plus 2. So that's k plus 1 squared times k plus 2. Let's see what we need to show. Oh, that's exactly what we need to do. Okay, you plug in k plus 1 here, you'll get k plus 1 squared plus k plus 1 plus 1. Let's write it in that way so it's more clear. K plus 1 plus 1. Okay, so you reached your right hand side. Therefore, by PMI, principle of mathematical induction, PM is true for all n in natural number. All right, any question? question? Is this clear? Oh, good. Okay, cool. Brief review, we'll do that later. I found an inequality question. We can do that. For step 3, how did you get from line 1 to line 2? This to this? Oh, this to this, we used IH. So we know from your IH, actually, let me just write down IH. And you know what I mean. 1 times 2 times 2 plus 2 times 5 till k times 3k minus 1 equals to k squared times k plus 1. This is your IH. So we used this. Oh, I'm on k here, not n. So we used this because here and here they are the same. So we know this term equals to k squared times k plus 1. That's how we did it. Does that make sense? Okay, let's do an inequality question. We can do this one. Prove 3n is greater than n squared for all n in natural number. Try this. Another one you can try is from the tutorial activity. For you can do prove 5 to the power of n is greater than or equal to 3 to the power of n plus 2 for all n in natural number. Okay, so we can do those two. Wow, it's been an hour already. I guess we'll either go overtime or we might. I said 6 to 8, right? So we actually might go overtime or we don't have time to cover everything. Do you guys want me to end at 8 o'clock or we just continue after 8 and try to finish everything? All the topics. Okay, cool. I'm fine with it. I just have a lot of marking to do. Fields. We can do field question as well. There is a question out, I think it's really good. A field question. It was on my term test when I took 102. So eventually we'll cover. I plan to cover every single topic, so it might be a really long review. But that's what I plan to do. And if I don't finish tonight, we can continue tomorrow. I can only do tomorrow morning though. It will be uploaded on YouTube. It will. Everything will be on YouTube, okay? Which topic would be the majority part of the test? I don't know. I don't know what your test look like. I suppose they might focus something that was never been tested before. Are you grading our test? I don't know actually. I suppose TAs with 2 tutorial sections are grading the test, but I don't know. So in that case, I will be, but I don't know yet. So I might grade one of the question, and I don't know which one. Anyway, let's finish those 2 examples. Do you guys mind if I skip the first few parts and just move on to induction step? Because I feel like base case and everything should be simple. Yeah, the first few steps should be okay. Okay, so let's only do induction step to save time. So you should have PN, you should have base case, and you should have your IH. Okay, so let's do induction. So what you need to show, let's write out what we need to show. We need to prove three to the k plus 1 is greater than k plus 1 square. So this is what we need to prove. You didn't know it's induction? What did you try? Are you trying to prove it directly? How do you prove it directly if it's for all and in natural number? Yeah, it's an induction question. Anyway, we need to prove this. So let's start from this side. 3 to the k plus 1. We can write it as 3 times 3 to the k. Why do I do that? Okay, why do I do that? This is because for your IH, you assume that 3 to the k is greater than k squared. So we know that we want to use IH. That's why I write it in this term. Okay, in this way, you see that we have something that's in the IH already. Okay, so that's why I wrote it like this. So now we can apply our IH. We know 3 to the k is greater than k squared. Okay, and we know this equals to this, which means this is greater than 3 times k squared by IH. Do you guys agree with me? Any questions so far? Okay, makes sense. Okay, so let's continue. 3 times k squared can be written as k squared plus k squared plus k squared. Now do you agree with me? Wait, I just realized this question is not a simple induction. It's actually a variation. That's awkward, but it's okay. I just realized it because for this question you need two base cases. So you need n equals to 1 and n equals to 2. Anyway, we'll finish it because we just have two more steps, okay? This is gonna be greater than k squared plus 2k plus 1. The reason is that for k greater than or equal to 2. Wait, do I need this? 2k 2. Oh, actually, it's fine. Yeah, it's fine. It's fine. It's not a big deal. K plus 1 doesn't work here. Yeah, but k plus 2. Yeah. You can think about it as a simple induction as well. I don't know how they define simple and variation, so it might be for k greater than 2. Sorry, for k greater than 2. K any questions so far for this step? Wait, let me calculate it. 2. So 4 plus 4 plus 4 is 12. If it's 2 to 4 plus 4 plus 1. Actually, if greater than or equal to 2 is fine. Yeah, greater than or equal to 2 is fine. Yeah, I thought it's greater than 2, then we don't need two base cases. We just need 1. If it's greater than 2, well, then we need 2. Why is this, okay? This is because k squared is k times k, okay, which equals to 2k, no, greater than or equal to 2k for k greater than or equal to 2, and k squared is k times k, which is strictly greater than 1 for k greater than or equal to 2. This is a reason, okay? Where we get 3 greater than 3? Where did you get that? I don't know where did you get that. Where did you get 3 greater than 3? I don't know where you got that. Yeah, this is 4.1. This is a simple induction. Are there no inequality simple induction? I thought inequality is simple induction. Is it not simple induction? Oh, it is simple induction. I thought it wasn't, but it is. It is. It is simple induction. I thought it's not, but it is. Sorry, guys. Okay, anyway, this will give you k plus 1 square as required. Therefore, actually, let me think about it. Ooh, do we count this as simple induction? Therefore, by P and by let me think. Okay, final conclusion, this is not simple induction. I'll tell you why. Because for simple induction, we still need two base cases. I'll tell you why. Because here, this proof, the induction step works only for k greater than or equal to 2. Okay? But for simple induction, you need your k can be 1 as well. But in this case, your k cannot be 1. So when k equals to 1, you cannot get this proof. You need k to be greater than or equal to 2. So that means p of 1 cannot imply p of 2. Okay? You can go on from p of 2 implies p of 3 and so on. That is why we need two base cases, because if you checked when n equals to 1 and when n equals to 2, everything else should be okay. But we know that p of 1 cannot imply p of 2, so this is not a simple induction. Because I tried it. Inequality can be on your term test, because a lot of inequality inductions are simple induction. Because here, it works only for k greater than or equal to 2. If you put 1 in there, it doesn't work. Here, it doesn't work for k equals to 1. (4.6.1) is simple induction. Would something with multiple cases come? Honestly, I don't think so. But I don't know how they think about simple induction. So I would say can't guarantee. Okay? I would think it's not simple induction, but who knows how they define simple. They might think this is simple as well. So can't guarantee anything. This might be on your test or not. I don't know. I really don't know. But the next one, let me think if the next one is simple induction. Yeah, this one should be definitely simple induction. So try this one. Sorry, let me remove this. Example 4 should be simple enough. Like, how do you define simple? Everyone has a different definition. Again, I'm gonna skip P and base case and IH. Let's do induction directly. So 5 to the k plus 1. Again, I'm gonna write it as 5 times 5 to the k for the same reason as before. Okay, because 5 to the power of k is in your IH. Thus, would be greater than or equal to 3 to the k, no, plus 2 the whole thing times 5 by IH. Yes, exactly, without the quantifiers. So your P of n in this case would be this. This is your P of n. IH part from the previous example. Here? Oh, here, because this is your IH, we know this is true. You multiply both sides by 3. We'll give you this. And 3 is positive. Multiply by a positive number for some no, that's not a quantifier. Let's just define quantifiers are things such as for all there exists. Those are quantifiers. So for example 4, we multiply both sides by 3. I'm just saying this is true because IH, we assume this is true. Why does this apply this? You multiply both sides by 3. Okay? Same here. We know IH is 5 to the k is greater than or equal to 3 to the k plus 2. That's your IH. So we know this is true. You have this, so you know that this is greater than or equal to this. Basically, multiply both sides by 5. Okay, let me just continue. Otherwise, we'll never finish. This equals to what does this equal to? This equals to 3 plus 2 times 3 to the k plus 2. I'm just writing 5 as 3 plus 2. Okay? The reason we do that is that we want to reach 3 to the k plus 1 plus 2. So in this case, you have 3 to the k plus 1. So you open a bracket, you'll get 3 times 3 to the k plus 2 plus 2 times 3 to the k plus 2. This is greater than or equal to 3 to the k plus 2. Since this is greater than 0, I feel like this step people might not understand. Any question from here to here? So I'm just saying that this is positive. Since this is positive, since this is non-negative, if you remove this, the term is gonna be smaller. That's all I'm saying. Any question? Yeah, because you are talking about inequality. Oh, actually, this is strictly greater than. Yeah, can never be 0. Well, it's greater than or equal to includes greater than, so it's fine. How did you get from the third line to the second last line? Third line to the 1, 2, 3. Oh, here to here? Wait, here to oops. Here to here? You distribute it 3 times this plus 2 times this. Does that make sense? Distribution law, remember? Okay. I removed it because we know this is strictly greater. This is greater than this. Okay? Actually, I want to use this. It's the same. It's not the same, but this includes greater than. Okay? Just be safe. Well, now you can open the bracket. You'll get 3 to the k plus 1 plus 6. No, it's not complete. I'm continuing. Eventually, you want to get 3 to the k plus 1 plus 2, remember? And we know this is greater than or equal to 3 to the k plus 1 plus 2. Now it's done. Now we show that this is greater than or equal to this. Any question? Because why it's this? Because we want this. That's why I wrote it here. I want to explain this. This and this. Okay? This means greater than or equal to. Or equal to. I could use that, but I could use that, but the reason I'm using this is because the question wants this. I could use that, but I was worried that if I use this, you guys eventually will write this is strictly greater than this. So you remove the possibility of equal. It stayed where it needed to. Where did 2 times? Oh, I removed them. You don't need that part. Because you want this. You want this to be greater than or equal to this. This is unnecessary. We removed it so that this is greater than or equal to this. We know this is positive. Okay, so after you removed it, this whole thing would be greater than or equal to this. Because this is positive. I know it's greater because I know this is positive. Okay, that's a key thing. If we don't know if it's positive, then we don't know. If it's a negative number, then it's gonna be smaller. Any other question? Okay, I think that's it for induction. Let's move on to the next. Why? Okay, let's say this. Let's say we want to show. What do I want to show? Let's use numbers so it's simpler. 5. Oh, no, let's use this. Now we want to show A is greater than B, and we know that actually A is greater than C, and we know that C equals to B1 plus B2. Does it work? No. B1. How do I want this? Okay. Change this to B2. We know C equals to B1 plus B2, and we know A is greater than C. Okay? Let's use this. We know A is greater than C. So let's start from here. A is greater than C. C equals to B1 plus B2. Let's write it in this way so that matches what I did. Okay? Oh, also B1, B2 are both positive. Okay, so you want to show this is greater than B2, so you need to remove B1, and this is greater than B2. Therefore, A is greater than B2. I removed this because we don't need it. You want to show A is greater than B2. I can remove it because B1 is greater than 0. So same thing here. I removed this because we don't need this. I can remove it because it's greater than 0, so I know it's greater than or equal to. Yeah, yeah. Alright, let's move on from induction. I feel like we did too much induction. Failed. Oh, let's go back, because I have some example questions that I never covered. Let's do this failed question. It is impossible for it to be 0. Wait, what are you talking about? What is impossible to be 0? For people who got it, let's try example 5 here. And for Nicholas, what exactly are you talking about? It's impossible for it to be 0, but remember I talked about greater than or equal to? This is greater than or equal to. So it involves greater than and equal. It's not greater than and equal to. So it includes greater than. Does that make sense? Okay, try this. I believe this was a quiz question or a test question. Test question, I think it was a test question. So for failed, we'll do 3 example. We'll do this one. We will do the one that was on my test, and we'll do another one. Okay. So this is a combination of failed and contradiction. Well, this is longer than I thought it would be. Move everything up. Wait. Okay, this is better. Oh, this is not multiplicative identity. This is reciprocal. Reciprocal. Contradiction. Okay. Do we have to prove a cube equals to a times a times a? You don't need to. That's definition of a cube. Also, reciprocal is the same as multiplicative inverse, right? Yes, that's another name of multiplicative inverse. Okay, let me explain what I did. So, since I want to show if a cube equals to 0, then a equals to 0. I want to use contradiction, so I suppose the negation of this. That's why I suppose a cube equals to 0 and a is not 0. Okay, so this is our assumption. And since I know a is non-zero, I know that its multiplicative inverse exists. Okay, so I wrote, since a is non-zero and it's in the field, there exists a inverse in the field such that a times a inverse equals to 1. It's because we know it's non-zero, that's why it has a reciprocal. Since it has a reciprocal, and we know that a times a times a equals to 0, we can multiply a inverse on both sides. That's gonna give you a times a equals to 0. Okay, you do some algebra in between, you get this. And from here, you can multiply a inverse on both sides again. So that's gonna give you a equals to 0. This contradicts with your assumption where a is non-zero. Therefore, this is true. Okay? The idea is simple, it's just some algebra in between. So this should be a simple field question. Do I need to write a conclusion statement like the statement if then it's true? It's better that you do, but I don't think we'll deduct mark if you don't. That will be too harsh. If that happens, I will talk to Daria and make them change the marking scheme. Okay, so I'll make sure you don't get you don't lose mark for not writing the conclusion sentence. Yeah, it's better that you write it, but if you don't have it, that's fine. It's not a big deal. Okay, as long as you reach the contradiction part, it's fine. Nobody cares about the conclusion. I should not say that. Anyway, any question about this one? Do we have any question? Let's continue for, so let me see. I did this. Okay, so let's do another contradiction question. And we'll do other topic.
Excuse me.
Yes?
Sorry, I do have a question.
Yes. For which question?
So, it's for the previous question.
Okay.
Yeah, the field one.
Okay, cool.
So you said that since A is not 0, and then, because like you assume that A is not 0, right? And then, and A is in the field, there exists a reciprocal for A, but then at the end you prove that A is 0, which means that there isn't a reciprocal for A. That makes
Which
A
means
times.
it's a contradiction. So since I show that A equals to 0, that means that my assumption is wrong. Does that make sense? So that means that what I assumed at the beginning is wrong. Therefore, the original statement is true.
Okay. Yeah. I think I got it. Yeah, thank you.
Any other question? Question. No? Okay, if no question, let's do a classic contradiction question. It's a classic contradiction question. Prove that the square root of 2 is irrational. This is a typical contradiction question. So let's try this. I'm kind of scared that if they give you something you've never seen before, you guys gonna freak out. So let's try to do something you've never seen before. Okay? Again, I'll give you some time to work on this, and we'll take it up. Try to find a more contradiction question that you've never seen before. But I would say your professor really likes. How do we know when to use induction, contradiction, contrapositive for direct proof? Okay, that's a great question. We'll talk about that later. Let me find another example. Let me find another example of contradiction first, and we'll talk about that, okay? Oh, this is a good one. We'll do this one. Let me leave it here. Last few. Did you guys hear my dog sneeze? Okay. Is this a field? No, this is a contradiction question. Oh, Here is a contrapositive question. Just want to mention, did I tell you? Did I say it? Oh, your professors, they really like even odd proofs, okay? So make sure you know how to express even numbers and odd numbers. Really important. I think I did this one. Did I do this one? I did a similar one, so skip that. Oh, this is a good question. This is a great question. We'll do this one as well. Induction. This is a good question. Okay, I found multiple questions. Let's do this one first. Well, did I just wrote proof that? It's proof that. Okay, here. Let's see the classic proof. For contradiction, suppose, what's our assumption, guys? What is our assumption? What do we assume? Rational, okay? Suppose square root of 2 is a rational number. Lazy is in Q. Okay? Since it's a rational number, we can write it as A over B. Okay, where A, B are integer, B is non-zero, and let's assume GCD of AB equals to 1. You're too loud, Bonnie. Give it too loud. Okay. Now, what do we do? What do we do, guys? Square both sides, exactly. So this will give us 2 equals to A squared over B squared. And what do we do? Get rid of the denominator, exactly, okay? This will give you 2B squared equals to A squared. And what's our next part? Rearrange to make B squared. This cannot be in pieces. Difference of square. Does that work? Difference of square? Do we do even and odd cases? Do you think that would work? Guys, try what you said. Okay, try what you just said. Let me think if difference of square works. That's not what I have in mind, but let me think. Difference of square. Yes. Okay, someone said what I think. Okay, this means that a square is even. Okay, because a squared equals to 2b squared. That means a squared is even. B is an integer, okay? This means a squared is even. A squared is even means a is even as well. Actually, this is, I kind of regret that I'm doing this proof, but because something is missing here, why is this true is missing. You will learn it later. It's a lemma. But you'll learn it later. But for now, suppose we don't need to prove it. Okay. I just want to show you something different, basically. So a squared is even implies a is even. Actually, it's pretty simple to prove. Let's prove it. How do I prove it? A squared is even means a is even. A times a. And oh, even times even is even. Yes, but what about the other? This is only telling you that a could be even. And what you did is saying that if a is even and a squared is even, but we need the other way around. Nicholas, yes, that's where we get the contradiction. Nicholas, what you are saying is when we get contradiction, so not there yet. I think one way you can do both are what you guys can do to prove this, you can discuss cases. So let me just write need a proof. You cannot say it directly. You can need a proof. Need to prove. We'll do that later. Let's suppose this is true. Oh, you're too loud, Ronnie. Let's suppose this is true first. Since a is even, we can write a as 2k, where k is an integer. Okay? Then you can write 2b squared equals to 2k squared, which equals to 4k squared. That's gonna give you b squared equals to 2k squared. Okay? So that means our b squared is even as well. Okay, b squared is even implies b is even. Now we have a and b both even. Then GCD of AB is now 1. This contradicts GCD AB equals to 1. Therefore, square root of 2 is not rational. Yes, they are relatively prime. That's what GCD AB means. So this greatest common divisor of AB is 1. So their AB are relatively prime, or A over B is in lowest term. They all mean the same thing. Yeah, I don't think it works. To be honest, I don't think it works. Okay, go back. Let's prove this, because this is missing. Side proof. Let's prove this. If A squared is even, then A is even. How do we prove this? Oh, what about no common factor? They do have a common factor, which is 1 though. Contradiction. Yes, you can use contradiction. I think, let me think. I think instead of using contradiction, contrapositive might be better. So suppose that contrapositive. So let's prove the contrapositive. If A is odd, then A squared is odd. Oh, this is a good practice for contrapositive. Okay, so suppose A is odd, which means you can write A equals to 2k plus 1, where k is an integer. Then A squared equals to 2k plus 1 squared, which equals to 4k squared plus 4k plus 1, which equals to 2 times 2k squared plus 2k plus 1. So this shows that A squared is odd. Side proof. Would they give us a multi-part proof like this where you have to prove something within a proof? I don't know. It has happened before on my quiz. So when I took one of the quiz question, it was an induction question. You need to do induction twice. So I don't know. I don't think so. It's very unlikely, but it's possible. Okay, it's possible. Okay. Any question about this proof? So this is a good contradiction question. Another good contradiction question that got a lot of students did it wrong is this one. Then I'll let you guys try this. So there are 101 buttons of up to 11 different colors in a box. Show that either there are 11 button. Oh, did I spell it wrong? Of the same color in a box, or there are 11 buttons of different colors in a box. This is a great question. It's from one of the exam. Okay, it's an exam question, which could be on your test as well. Let's try this. Yes. Try this question. It's a great contradiction question. Okay, here is a hint. The hint is use contradiction. While you guys do that, I'll write down the question of. I'll give you a few more questions to practice. Okay, the extra practice question is a induction question. I'm not gonna take it up, but you can try it at home. Image. I wanna do an image question. And we should do set question as well. Okay, anyone got the contradiction question? Should I give you more time to think about it? I'll give you 3 more minutes to think about it, okay? The key of this question is you need to get your assumption right. So as long as your assumption is right, the question is really simple. But getting the assumption correctly is not easy. No. The student who PM'd me, it's not correct. I'll be back. There are no and there are no. Think about what does it mean for there are no. Can you rephrase it? Neither are there. Okay, let me see. Can that give you anything? You can use this assumption, but I don't think it's gonna give you anything. What do you do next? Okay, let's take it up. I feel like everyone's stuck. Let's take it up. Proof. For contradiction, assume, okay, our assumption. Either something or something will give you both something and something. Okay? So assume that now we need to negate this. Negate there are 11 buttons of the same color in the box. So some of you said there are no 11 buttons of the same color. But what does that mean? No 11 buttons of the same color, which means that we have at most 10 buttons of the same color. Do you guys agree? Up to 10. Yes, up to 10, not at least 10. So there are up to 10 buttons of the same color. So assume that there are up to 10 buttons of the same color and up to 10 buttons of different colors in a box. Well, someone said, what about more than 11 buttons of the same color? But here you have up to 11 different colors. So that's not gonna work because you cannot have more than 11. Up to 11 means you could be 11. Does that make sense? But we don't want it to be 11. You want to negate a equals to 11. So it's less than 11, which means less than or equal to 10. Is this using contrapositive as well? No, this is contradiction. This is contradiction. How long is it for? I don't know. We'll finish. We'll stop when we finish all the topics. Okay. Yes. For contradiction, you need to negate the original statement first. That's your assumption. The reason that we choose 10 is because here we want not equals to 11, and we know has to be less than 11. So basically less than 11, and since it's integer, is the same as less than or equal to 10. That's why we pick 10. So if you pick 9, what about 10? Okay? Because here it says up to 11. Yeah, you can leave anytime you want. I'm recording everything, so you don't have to stay here for a long time. You don't have to stay here all the way to learn. You can leave anytime you want. Why not greater than 11? Because here, up to 11, okay? So 11 is the biggest number. Yes, exactly. That's our next step. So since we have up to 10 buttons of the same color and up to 10 buttons of the different color in the box, The maximum you can get, maximum filters are 10 times 10 times 10 colors per bottom. Wait, 10 colors, sorry, 10 colors. Wait, how do I, well, why is it 10 bottoms? 10 colors per, oh, 10, we have 10 colors per button and we have 10 buttons per color. Just use 10 times 10. Too complicated. 10 times 10 equals to 100. So the maximum buttons you can get is 100. So that's a contradiction. Okay. Extra practice, we're not gonna do this contradiction. We did a lot of contradiction, contrapositive. So we'll move on to the next topic. What do we want to do? Let me check. What do we have? Let's do a set question. Actually, let's do this one. A set question, because people are pretty weak on this. So prove that this is a set question combined with contradiction. Okay, prove that there are no sets A, B, and C such that A intercept B equals to the empty set, A intercept C is the empty set, and A intercept B minus C is the empty set. I feel like you guys didn't do much questions like this. Basically, every set question you got was set identity question. So a lot of people are weak on those type. Image AGM set. Yeah, we'll do image next. We'll do image next. This is a set question. I think people are pretty comfortable with set identity questions. Are you guys comfortable with set identity questions? Yeah, okay, cool. So we're not gonna do that. The only thing I'm worried about is Cartesian product. So set question involves Cartesian product and set question involves function. But I did those questions in my previous tutorial or previous video. So I'm not gonna do them again. For set, we'll do this question and we'll move on. Let me just tutorial 6. Sorry guys, I want to check something. Can continue. I do this. Tutorial 4. Yes. So I want you guys to know this one. This question, please know how to do. So tutorial for let me write it down. For more stats question, check tutorial 4. Okay, so please make sure you know how to do normal set identity. You should know set identity of Cartesian product. So I did one example in tutorial 4. And you should know set involves function. I did one example in a video. It's called set identity involves function. So make sure you know how to do all of them, okay? You never learned Cartesian product question properly. That's sad, to be honest. I covered one question in tutorial 4, so you should check that, okay? So this question, I'll show you again. This question, make sure you know how to do this, okay? This question. Make sure you know how to do this. But we'll talk about Cartesian product again later. We'll definitely talk about that. Oh, for stats, you should know how to draw them out as well. Okay? That's another one. Which tutorial is that? 2, 3, 2 tutorial. Let me check. Don't remember. Yeah, tutorial 2, activity 2. So make sure you know how to do that as well. This is tutorial 2. Check that. Okay, so this question, I'll write down my proof and I'll explain. Wait, hold on, let me think, how do I do this? Assume that. Oh, yes, they are the same thing. A intercept B minus C. That means X is empty. Oh, that's why I was like, it doesn't make sense. Typo. Here is not empty. Correction, here is not empty. So sorry if you get stuck for a long time. Here is not empty, okay? A-intercept B is not empty. Since A-intercept B is not empty, okay. So for contradiction, we assume that there are such sets A, B, C, such that A-intercept B is non-empty, A-intercept C is empty, and A-intercept B minus C is empty. And we know that A-intercept B is non-empty. That means that we have an element in there. Okay, so I assume that that element is X. So this means that since this is non-empty, there exists X in A-intercept B. Since X is in A-intercept B, that means X is in A and X is in B. And since A-intercept C is empty, and we know X is in A, okay? We know X is in A, and we know A-intercept C is empty, which means we don't have any element that's in both A and C. Okay, we don't have any element that's in both A and C. And we know that X is in A already, so it can never be in C. This might be a little bit complicated, but any question so far? Any questions so far? Question? Isn't there a contradiction at the middle? Where is a contradiction? Where is a contradiction? X is in A and X is in B. Okay? And if the last statement is true, X must be an element of C, which is contradiction to previous. If the last statement, you mean this one? Yes. If this is true, then X must be an element of C. Why is that? Why is that? You need to explain why, okay? What you said that claim is not obvious, you need to explain why. But don't, because we were saying X is in A and X is in B, but don't we say X is not in A? I didn't say X is not in A. Where did I say X is not in A? X is in A versus X is not in A. I didn't say X is not in A. Where did I say X is not in A? Oh, I see. A intersect C is empty does not mean X is not in A. It means that X cannot be in both A and C. So let's draw the Venn diagram. So let's say this is A, this is C. A intersect C is this part. Your X can be here, it can be here, but it cannot be in the middle. So it could be in A, it could be in C, but it cannot be in both A and C. So A intersect C is empty does not mean A is not in A. Okay? But from the previous step, we know that X is in A. Since we know X is in A already, it cannot be in C. Okay? Because we know it's in A already. And the intersection is empty, that's why it cannot be in C. Because if it's in C, then it's in A intersect C. Okay? Anyway, this showed us X is in A, X is in B, and X is not in C, which is exactly this. A intercept being minus C. So this, since we have an element in this set, that means it's not empty, which contradicts with our assumption. Okay? Any question? This is a good question. I think this is a really good question to test your understanding for sets. And it's not a set identity question. It's not a normal set identity question. Okay, any question? Okay, cool. Let me see. What did we do? We did induction, we did contradiction, negation, and those things I don't wanna do them because when we do contradiction and contrapositive, we did a lot of negation already. So I'm not gonna cover that. I wanna do image. Yeah, I wanna do image questions. Let's do image questions. Here. Image question. Let's talk about what image means. So if we have F mapped from A to B, and let's make something up. Let me see if I can find a good function. A good function. What is this? Let me try to find a good function. Give me some time. Why is it making you more worried about the test? Wow, seriously? Okay, now I'm worried too. What about the rest of you? Did you finish? Wow, uh you get it. Okay, cool. You got one. Okay, this is bad. This is bad. Huh. Wow, okay. Okay. Yeah, I feel like you might need a break. You might need a break to digest everything covered so far. Let's stop here. What about this? Let's stop here and we can continue tomorrow. I can do 10 to 12 tomorrow. That's the only time I can do. Does that work for you? It's recorded, yes. It will be recorded as well. Tomorrow it's gonna be recorded as well. So tomorrow I hopefully that's not gonna take us too long. So I will do statements because there are some questions that are really good. I'll do statement. I'll do AGM. We'll review inequality. We will do AGM. We'll do what else? Function, image, such questions. Okay. You memorize the notes. You don't memorize anything from the course. You don't memorize anything. Please do not memorize anything. Memorizing is not gonna help you. You need to understand why we're doing each step. Okay. Can you recommend to find more image? Are we going to do expert as well? Oh, even the proposition axioms? Well, you should know the proposition and axioms, but I'm just saying you should not memorizing any proofs or any solutions. We can do extra practice tomorrow as well. Where to find more practice? You can find some practice on my Quarkus page. So I posted some. Where else? You can Google some. Before the word problem. Let me see. I didn't do any image question today. This is not an image question. Are you talking about this one? This is not an image question. This is an induction question. This is induction combined function question. Okay, so let's stop here. We will continue tomorrow from 10 to 12. I will upload the recording. Tomorrow, office hour will be recorded as well. Okay, so tomorrow I will try to cover all the topics that we didn't cover tomorrow, and hopefully that's gonna help you study. Yeah, I feel like it's been too long and you guys might not be able to digest so much. So make sure you understand what we are doing. YouTube. I will post the link on my Quarkus page as well. Okay. Any other question before we end? B combination. It's possible. I think a lot of professors they like to mix them up together. It's possible. Okay. Cool. Let's continue tomorrow. Have a good night. I hope you can sleep well after the office hour. Hopefully, I didn't ruin your confidence. But yeah, I'll see you guys tomorrow. Okay. Stop recording.